here I'm just going to talk about some very recent experiment and also simulations that we did for on the topic of complex Soliton dynamics. And I will not go in detail of how the simulation works, because that is actually it's pretty easy to understand. You can just sort of change the versions that Miles did for pulse pumping, and it's pretty easy to understand. But I will just show you that the single LLE model that we use the whole time is actually extremely powerful to even capture the very delicate and transient dynamics that we actually observed in experiments. And this is, I'll show you. And this experiment, this project is a collaboration between EPFL and also CSEM in Switzerland, and also University of Geneva. So as Miles just talked about, pulse pumping, right? Essentially, if you think about it, what's pulse pumping? Pulse pumping in the frequency domain is essentially just to use a narrow bandwidth comb to generate a broad bandwidth comb. Is that correct, right? So let's say the narrow bandwidth comb probably contains 10 or 20 comb lines, and the generated Soliton comb probably contains, like 500 or even 1,000 comb lines. So the narrow bandwidth comb, you can think it as probably 20 or 10 lasers simultaneously pumping the resonator, correct? Now, okay, let me ask you a question. What's the most simplified, the most basic version of pulse pumping? Probably the narrow bandwidth comb you use only contains 2 lines. Is that correct? Right, okay. So what's the temporal form of the 2 lines laser pumping the resonator? The 2 lasers, right, they pump 2 separated resonances, and in the intracavity field, these 2 lasers beat with each other, causing a sine wave modulation, correct? Right. So this sine wave is essentially the very basic form of pulse pumping, except this pulse, this sine wave, is not a very narrow, short duration pulse. It's a sort of a fat pulse, correct? Good. Now, this all makes sense. But now let's change the perspective a little bit here. Let's think about this, right? First, we use one laser to pump one resonance to generate Solitons. And what if then we use another laser to pump another resonance, right? These 2 lasers do not need to be synchronized or do anything. They can just do that one by one. And let's generate one Soliton with one laser and generate another Soliton with another laser. And these 2 Solitons do not have to be the same. Does that make sense? Actually, I don't know, because it seems sort of a little bit not so easy to understand if you consider the pulse pumping, because pulse pumping essentially uses so many lasers to generate one single sort of kind of Soliton, right? They are not like 20 different Soliton species. They are just one type of Soliton. So the answer is not so obvious here. But let's consider this picture here, right? We use one laser to pump one resonance here, and this the laser cavity detuning is this delta 1, and that probably can, maybe cannot, but maybe can generate the first. Oh, of course, it definitely will generate the first sort of kind of Soliton, and then we put another laser in, and this detuning is delta 2, and of course, you know that the Soliton, the power, the duration, and everything depends on the laser cavity detuning. So this delta 1 and delta 2 doesn't have to be the same. And then this laser can generate a different type of Solitons, and they will coexist. These 2 kinds of Solitons will coexist in the cavity, right? So now, if let's assume that it can work, then there are 2 possibilities. First of all, because dispersion, right? So you pump 2 resonances at different wavelengths, and the dispersion, which means the local free spectral range, the Soliton group velocity doesn't have to be the same. So essentially, these 2 Solitons will travel with a slightly different speed, right? So what would happen? The soliton sooner or later they will meet each other, right? And when they meet each other, so two things, let's say they don't die during this collision. So two possibilities will happen. One, they probably will bind to each other, and they do not cross each other anymore. They will travel with the same speed as an entity. Or the second possibility is that they will keep their respective their own speeds, and then they will keep collision each other the whole time, right? So let's do some simulation first. Now, first the simulation is this very basic pulse pumping, form that we essentially just actually we didn't do that. This Stephen Webnitz in Italy did this simulation. So they used the two lines to pump two resonances. Of course, these two lines doesn't have to be to pump two resonances that is close to each other. They can sort of far away from each other. So if the two lines, there are like 20 FSRs in between them, then essentially you would just create a sine wave, but this intracavity round trip will contain 20 periods of the sine wave, right? And then these pulses can be generated on top of each sort of this fat pulse, right? So it is the exactly the basic form of pulse pumping, and you can definitely use the Miles method on pulse pumping to simulate this. Actually, it's even simpler because it only uses two lines, right? Now, the second situation here, right, will show you. We use such two lines, two lasers, but because these two lasers would have very different cavity laser detuning, so I can just set the two lasers the laser cavity detunings to be vastly different, and then we can pump the pulse one by one. And what we see here is at first, when the two lasers move into these two corresponding resonances, first of all, the first laser, well, because their laser cavity detuning is so different, so at first, one laser will generate soliton first. Here, generates the solitons with the CW laser, makes sense. And after some time, the second laser will also approach and get into the second resonance and generate the second kind of solitons, right? And because, as I said, these two solitons generally would have sort of different group velocities, so they do not go in a parallel way. They will crash into each other and probably meet, and then form sort of bound states. As I said, they will move together, right? As the simulation show here, if you can see the second wave of pulses after some time will meet the first wave of pulses, and some of them will form a bound state, and they will travel with the same group velocity. Okay, so this is simulation, and we did the experiment. We used two lasers, just like that, pump two resonances, and here is our experimental results. So we use two lasers. First of all, we set these two lasers just to pump two neighboring resonances, and then we sort of increase the frequency gap between these two lasers to two resonances, three resonances, to two FSRs, three FSRs, which essentially just sort of increase the number of periods in the sine wave periods in the intracavity round trip, right? So what do we see here? Okay, what do we see here from the comb spectrum? We sort of, especially from this one and this one, you can see that it's actually it's a dual soliton state, and plus a small single soliton state, right? And this one also is a dual soliton state plus a single soliton state. And we also, I'm not going into details of these experimental results, but here we use a sort of transfer function measurement to actually definitely prove that there are two kinds of solitons coexisting in the intracavity field. Okay, so it actually works. But now the question is, are they bound states, like I said, traveling with the same group velocity, or maybe they do not bond together, they will keep collision into each other. So what we did here is we measure the repetition rate of this comb, and we found there's only one repetition rate, meaning that they do have these two combs, right? The first Soliton comb and the second Soliton comb, they do share the same repetition rate, which means they do exactly form a bound state. Okay, that's good. Now, let's keep increasing the frequency gap between these two pumping lasers. In this way, right, because of the local dispersion changes, then the group velocity, the natural group velocity of soliton, the difference between these two solitons, is supposed to be increased, and if there's some limit there to separate these two situations, one is the bound state, the other is the unbound collision state, then it probably can. We can probably demonstrate the collision if we increase if we separate these two pump lasers, right? Now, this is what we do. Now, in this case, right, we use these two lasers, but there's a sort of a large frequency gap. We pump the same resonance family, but these two lasers, there are like 47 FSRs in between these two lasers, which is sort of, one FSR is, in this case, is 14 gigahertz. So 47 corresponds to 2 or 3 nanometers, something like that. Okay, so in this case, what we observed here, right, this is a repetition rate spectrum, and we see that there are two major repetition rates, which means that now in this case, these two combs have different repetition rates. And also we can see there are many sidebands. And these sidebands, as I will show you later, are caused by the collision situation, because the collision, during this collision, these two different kinds of solitons will cross each other and interact with nonlinear effects, and these interactions will cause small modulations that is manifested by these sidebands. Okay, so here is a simulation that we did. Just to use the LLE model, except unlike the pulse pumping situation, we use two lasers, but these two lasers would have sort of large detuning differences, right? So we actually, we generate two solitons. One is this one, and the other one is here. And you can see here that because the repetition rate difference is kind of large, so they do not bond anymore. They do not bind anymore. But the periodic collision can happen, and even with such collisions there, these two solitons still can survive and live long, prosper. So here we just we monitor. We pretty much like take this simulation here, and we monitor the intracavity power fluctuation, right? And we see that upon the collision event, this intracavity power will show strong fluctuations, which is due to the soliton interaction. Now, this is some fancy experiment we did. Also, I do not have time to go into the very details of the experiment, but we can directly image the Soliton interactions with this experiment, and we can separate these two different kinds of solitons in real time and look at their power fluctuations. So this is one type of soliton, and it's a dual soliton state. And this is another type of soliton that is single soliton state that is generated by a second laser. And these two solitons have different group velocities. And at these points that are denoted by the red lines, they overlap in the temporal spatial space, which means that they cross each other, right? It's a collision, and we look at what the intensity of each soliton upon the collision, and we see that each solitons will show power fluctuations. That of course is what we expected, but the most important thing is that if we look at the power fluctuation oscillation, right, this oscillation, you will see that these two different kinds of solitons will exhibit very different oscillation periods, oscillation frequencies, right? So this is a unique feature of dissipative cavity solitons, is that each soliton has this kind of called soliton relaxation oscillation, and it was a very accurate theoretical explanation of such thing is still not completely understood, but it's widely accepted that each soliton has one unique relaxation oscillation frequency. So two types of solitons, they will have two different types of relaxation oscillation frequencies. Now, we can get pretty much the frequency of these two oscillations, and we compare these oscillations with the simulation, the power fluctuations that we get from the single LLE simulation, and what we get is that these fluctuations exactly contains two different type of oscillation frequencies, which is very close to the experimental observed ones. Okay, so LLE is really good, right? Great. Now, this is just a more experiment. In this experiment, what we did is that we changed the laser of one laser while keeping the other laser stable. So basically, what we did is we changed the group velocity of one soliton, and with a very carefully chosen the frequency separation between these two lasers, we can show that at first these two solitons form a bound state, and then as we sort of change the natural group velocity difference between these two solitons, there's the limit. The limit has been broken, and we sort of cross the boundary to the collision regime, and then two different repetition rates show, and we can see these power fluctuations that is due to the cross-phase modulation, the soliton collision. Okay, so also this experiment can also be simulated with very accurate results by the single LLE modulation. Okay, so all these experimental observations can be simulated with one single LLE based on the sort of a simplified version of the pulse pumping that Miles talked about. Now, there's one particular situation that could be worth thinking more, is that what if we use 2 lasers to pump 1 resonance, right? If you use 1 laser to pump 1 resonance and generate 1 Soliton, and then we use a second laser, but we use that laser to scan across the same resonance, because these 2 lasers doesn't have to have the same laser cavity detuning. Is that possible? Of course, it's possible, but what will happen here? And of course, the most important question to this workshop is how to use LLE to simulate such a situation, right? So here is the situation that I just described. We use 2 lasers, right? These 2 lasers are sort of, pretty close to each other. They are not like more than 1 FSR away from each other. They are pretty close to each other, and they pump 1 resonance, one after another, right? So this is just sort of like what you saw from the earlier situation. That is, first the laser generate the solitons, and then the second laser gets into the resonance and generate a different type of soliton. And these 2 solitons, naturally, they will have different group of velocities, and they will form bounded states. So the simulation still works, and we also so a little bit of trick here is that because in the pulse pumping situation, we have this assumption that each comb line that we input into the cavity will pump 1 single resonance. So we basically what we did is we define such a comb in the frequency domain, and then convert that into the time domain, and then let the LLE run, right? So, but in this situation, because these 2 lasers are essentially pumping the same resonance, so actually it's even simpler. What we did is we consider the second laser as a sideband to the first laser, and the frequency difference between these 2 lasers are pretty small. So what we did here is we just add 1 sideband expression into the pumping term, and this sideband, because it's the frequency difference from the first laser is small, so this sideband contains basically contains a term that is a function of the slow time. So it's just a modulation on the first laser, because what experimentally how to generate sidebands basically use either amplitude modulation or phase modulation, or the combination of these 2 to generate sidebands, right? So you added different types of modulations to create sidebands. So here is what how I create a sideband in simulation, right? So it's still a slow modulation. Now we use such a simulation to simulate the different compositions of these molecules, and we compare to the experimental results. As you can see, right, the agreement is pretty fascinating, and all the time, right, we only observe 1 repetition rate, which means that they do form bounded state, because these 2 lasers are pumping the same resonance. So these 2 solitons, they will have slightly different group velocity, but their natural group velocity still is very close. So the natural group velocity difference is not large enough to break the limit the limit of bounded state. So they will not form Soliton collisions. They will form bounded state. Good. And this is the experiment setup on the imaging, and we use this technique to image the Soliton dynamics, and we can, essentially we just use a sort of a different pulse lasers, And this pulse lasers is sort of sampling the Soliton comb, that the Solitons. And with these samplings, we can, for example, in 1 millisecond, we can record tens of thousands of round trips. And by averaging such a large amount of data, we can get pretty accurate the temporal separations between these two kinds of solitons. And we also, because it's averaging over a large amount of data, so the standard deviation is pretty much less than 10%, which means that the result is very trustworthy. So, and this is experimentally measured separations between these two different two different kinds of solitons, and they are usually a few hundred femtoseconds, less than 1 picosecond. And so here we did a simulation in the temporal domain, and these are the simulation results that we get. So you can see that the disagreement between the simulation and the experimental results is not very large, right? They are like maybe 10 or 20% deviations, but this simulation is pretty accurate. Okay, so now let's ask ourselves a more fundamental question. What is the reason for the Soliton interaction, right? If you think about the LLE simulation, if you still remember the very fundamental of LLE, it corresponds to a large amount of equations in the frequency domain coupled to each other, right? So, and the coupling term contains cross-phase modulation, self-phase modulation, and also most importantly, the four-way mixing terms, right? So, but in this situation, because these two lasers will have very different carrier frequencies, so which means that this two solitons carrier frequency is very different. So if there's any four-way mixing, and the four-way mixing terms depend on the phase difference between these two pulses. So if the four-way mixing terms plays important role, it's a very fast variation, sort of like a rotation term. And I assume that in this situation, such fast rotation will be averaged out. So I simplify this case, right? We thought that this Soliton binding mechanism is only caused by the cross-phase modulation terms. Okay, so cross-phase modulation term doesn't depend on the phase. It's an intensity-dependent effect. So here is what I did. I sort of use one LLE to simulate one soliton that is pumped by one laser, and then use a separate LLE to simulate the second soliton that is pumped by the second laser. So they are separated, but there's only one coupling mechanisms in between. Okay, that is the cross-phase modulation that I put here. So if you know how to simulate one single LLE, then this is pretty simple. You just add a second LLE in the same numerical simulation propagation package, and all you need to do is you just add this coupling terms to each equation. And because now I'm simulating two LLEs, right? So I can sort of separate the two solitons. And this is the first soliton, and this is the second soliton. And we compare to a single LLE that contains both solitons. And we find, when these two solitons, they meet each other in the spatial temporal domain, they will form bound state, which is exactly what we observed from the single LLE simulation. Okay, and we also compare the results, the final form of the Soliton bounded states that we get from the single LLE and these coupled mode equations, and they are pretty close to each other. So that means this simplification I made that assumes the cross-phase modulation is the most important and dominant mechanism in forming the bounded state is correct. Okay, so the other effects such as four-way mixing is not very important here. Okay, so that's it. And just for your information, this coupled mode equation simulation, as well as the molecule. So this simulation to generate molecules by pumping one resonance with two lasers will be provided to you with MATLAB files. So if you have MATLAB, you can just click one button and run the whole simulation by yourself, and you can analyze in detail. Okay, that's it. Thank you.